Testing. Testing. Make sure this audio works before we start talking. Okay, audio seems to work. All right, everybody, welcome to another Hoopo stream. We're working on the scroll prize again today. We got a bunch of stuff planned for today. If you're just joining, the scroll prize is a challenge where you basically try to detect these the presence of ink in X-ray scans of these ancient scrolls. So basically, it's a binary classification problem within the computer vision sphere. And before we actually do any additional development or anything, we are going to review the results that we ran. So this right here that you're looking at is a TensorBoard, which is basically a visualization tool that allows you to see runs. So anytime you run a machine learning job, you can see these runs, and you can see the loss goes down over time. There's a whole lot of them over here. And the dice score, which is what we're evaluated on, goes up over time, at least for most of them. So you can see here how this is obviously kind of overfit, because it turns out that the test data is the train data. I just discovered this a couple days ago, but apparently the testing data is literally pieces of the training data. So it makes sense that we're going to have an overfit situation where the dice score is going to get up to almost like 1, right? 1 would be a perfect dice score. So don't trust this dice score because it's kind of overfit and it's not necessarily the best. How's it going, Siege? All right, so what do these actually look like? So this is what the predictions look like. So for every single model that we trained, and we sweeped across a kind of a broad range of hyperparameters, we asked the model at the very end to predict on the test data set, and then we can kind of see which models did well, which models did poorly. And you can see that we have some here that are doing good. You know, so you look at this one. This one seems like it's making some solid predictions here, versus something like this. This one is making no predictions, right? Yeah, that is true. The test data is the training data. I did not notice, but I literally spent a whole week and I didn't realize it. But if you actually look at the data that they gave you, this training example, you see how this little fragment piece is like this? Let me make this a little bit bigger so you guys can see. But this fragment piece, if you actually go to the test, it's the same thing. It's just the top part of it and then the bottom part of it. So yeah, one of the things we have to do today is separate it out, because we can't be using the test data in the training data set, because or else these dice scores are meaningless. So we're gonna have to basically take it out. I'm thinking what we can do is create a test data set that is basically the bottom 20% of all these trained data sets. Yeah. But I don't know. We'll see what happens. Okay, so we have some runs. We have some of them that are working well, other ones that aren't working well. And because we sweeped over such a wide variety of hyperparameters, we want to know which hyperparameters are doing the best. So you can see here in the hparams tab and parallel coordinates view, this is one of the more useful views here. And you can add additional parameters here. It doesn't look like image augs is anything, but every single one of these lines represents one training run, right? So let's see, we can num samples, the model, the num epochs. Let's get rid of image augs. Where's that? I think this is a good one too. evaluate. How about use GELU? Okay, so now we have all of these runs, and here at the very end, the dice score, this is the actual score, right? And yes, technically it's like overfit, so it's not actually a dice score of 0.9, but it's still useful as a kind of a proxy to see what learned and what didn't learn. So what you can do is you can basically highlight just this part here, and TensorBoard will show you, okay, which of these runs were the highest performing runs, which of these actually did stuff. So one of the first things you can notice here is that the num samples, which is basically the size of the data set, none of the runs that had 10,000 had a high dice score. But if you look at all the ones that scored very low, lots of the ones that had 10,000. So this is telling me that the size of the data set is very important, right? And obviously, as you could have probably intuited, the bigger the data set, the better the performance. So if you actually see here, at some point, you need either 120,000 or 60,000 num samples. So one thing that we're learning here, bigger data set helps. Another thing here, if you look at just the top, you notice how use GELU is all false. So that's telling me that the GELU activation doesn't actually matter. We were doing a GELU versus a ReLU activation on the final layer, the classification head, and it doesn't really seem to do good stuff, right? It seems like no GELU is used in the best solutions. All right, let's look here. Num epochs. Similar kind of story with the dataset size, how only the highest number of epochs resulted in the highest score. So all the models that trained for 8 epochs versus 16 epochs, the 16 epochs beat them. That's telling me you train for longer, you get better results. All right, and then what about the model here? We have the model is ResNet 50, ConvNext tiny, ConvNext small, ConvNext big. These are still relatively small. I think another thing we should do today is try some larger models. I think these small models are kind of, we're getting to the capacity of these small models, and if we want to kind of push our score, we need to get larger models in here. But we're noticing that the, for example, the ConvNet small does better than the ConvNet tiny, which makes sense. It's bigger, but this ConvNet base just not really doing great, you know. You would have thought the biggest model would have done the best, but really it's this ResNet 50. Next thing I'm looking at here is the freeze. So this is either where we're either freezing the pre-trained encoder here, this model, or we're not freezing it. So freezing it means we're using the pre-trained weights, and all we're doing is retraining the head. If we're not freezing it, then what we're doing is we're pushing gradients into that model. So these models are so small that even if we don't freeze them, right, and we don't use the pre-trained weights, they basically end up overfitting to this tiny, relatively small data set. So I think that's why we get these high dice scores with not frozen models, is because the overfit model is actually pretty good for this particular regime. But yeah, that's kind of what I'm gleaning from this, right? If we go back to our scalars, actually this, let's see if we can find one. Ooh, this one, weird, something happened there. Let's see. I feel like this one is very clean. Like that one. I also like this one. This one looks very clean as well. So can we use this model here? 29D55, right? So we can go into our output directory here. Image output, and we have 29D51. 29D55. Here we go. That's our predictions. They're a little bit noisy. Another thing we're doing is we're resizing the images. Like all of these are on small resized versions. What are my next steps? So I think right now we're still sweeping, still figuring out what good hyperparameters are, but we're using very small models and we're using a small subset of the data, and we're also resizing very small. So I'm not using the full sizes of the image. If you actually go to the data set here, right? These images are huge. They're 9,000 pixels by 14,000 pixels, right? So it's actually it takes a long time to load these into memory, and then it actually will break if your computer doesn't have enough memory to hold it. So right now what I'm doing is I'm using resized versions of these images that are 10% of the size, right? But the problem is that 10% of the size also means you're losing a huge amount of the signal, right? So I think that's definitely holding us back. We want to be using larger image sizes, and we also want to use a larger model, and we want to train it for longer. So all of the kind of power law stuff we want to improve on. Model size, dataset size, training time, and the dataset resolution. The problem is that as soon as you increase any of those, it becomes a lot harder to sweep because every individual trial takes significantly longer, right? Whenever you're doing these hyperparameter sweeps, it's sometimes you want to actually use smaller models, smaller data sets, smaller resolution, so that you can actually sweep over a larger array or a larger amount of permutations of hyperparameters. Okay. So we were here, and we wanted to see if we could get the saved model for this one to actually work well. So let's go ahead and run that. So open up our VS Code. VS Code is everybody's favorite IDE. Let's make sure to git pull here. Already up to date. And we do have a notebook here. We called it eval.py. And we're going to do an eval from a directory. There is an available update. Let's download that later. Episode dir and output dir. So here, our folder is going to be home, tren, dev, Ash and Venus, output. Yep, that. This. And yep, sounds good to me as well. Let's actually put it in a new folder. Make a folder here. We'll call it preds. Put our predictions in there. Okay, so if we run this, we're gonna have to start a kernel here. Oh no. This is an issue. This is an issue. I think we changed some of the model and now we can't actually run it, unfortunately. Okay, screw that. Here are all outputs. Basically, the problem is that since we ran this sweep, I made more changes to the model, and then now we can't actually load it without that happening. So we're pivoting. We're no longer evaluating this model. What we're doing now is we are seeing if we can even train a model. So let's rename this folder here. Let's rename it to output 0404 24. And we'll make a new folder. We'll call it output. Okay. So close out of all this crap. Let's open up a terminal. This one. And let's just see if we can if the sweep still works. So let's run our sweep. This sweep.py. All this does is it basically chooses a bunch of hyperparameter values and then sweeps over them. Let's see. Let's give it seed 0 and a batch size of, let's do 8. All right, we need to activate our conda environment. Conda activate ashen penis. Go. All right, so here we go. We're trying with a bigger ResNet now. Our learning rate, input size, so we're using 224 by 224 by 65 versions. Okay, training. Now it's actually doing the prediction. So if we go into our output, all right, we have our model here. We already have our model.path, so we can actually probably already take this out here. So do this, copy this name, go back to our eval. That there. Run it. So it's taking a second here because the prediction image is actually quite large. And this is, so the title of this particular stream, I called it quantization, right? And quantization is a strategy by which you reduce the data type of the different parameters in the model. So a quantized model, instead of using something like a float 32, you can get it to where it's like a 16-bit or potentially even 8-bit, right? But the trade-off is that by reducing the precision, or by reducing the kind of size that each of the parameters in your model takes, generally you're trading off performance, right? So why would anybody care about making their model smaller and losing on performance? Well, the reason is that I was doing some more kind of inspection on this Kaggle competition. I was reading about Kaggle competitions and kind of thinking about it more, and it turns out that I think that most of the time, if you want to be kind of at the top of this leaderboard, you have to basically do ensemble techniques. So what does that mean? That means that you're not just running one model, you're running basically maybe 5 or 6 models, right? So you're using 5 or 6 different models, evaluating with every single one of them, and then the final answer that you predict is basically the combination of all those models, right? That's what an ensemble method is. It's basically using an ensemble of models in order to get a better prediction, right? But the problem is that these models are going to be pretty big, and these notebooks are pretty small, right? So the accelerators that you kind of have access to here, I think this GPU P100 only has like 16 gigabytes of memory, but more so than that, these GPUs have kind of like a limited amount of RAM and just memory and CPU in general. So I think it's going to be unlikely that we can get like 5 big models in here and evaluate on every single one of those 5 big models, because as you guys are noticing, even these small models that I trained evaluated on a small downsampled version of the original image is taking forever. You see here it takes like 6 minutes just to run eval on every single pixel. So I was thinking, okay, well, what if we quantized the 5 big models and then they ran quicker? Then we should be able to maybe get it to evaluate in a reasonable amount of time, right? Because also it has to run in less than 9 hours, right? So that's kind of where I'm going with this quantization, right? I want to quantize these models, not because it's going to lead to better performance, but I want to quantize these models so I can run more of them at the same time. But if we try to quantize these models and they significantly degrade in performance, then maybe we need to reevaluate the strategy of kind of using an ensemble of quantized models. So that's kind of the main goal today, is to figure that out, is see how much performance we lose by doing that, and see how much speed up we actually get. Okay, so if we actually go to our eval from episode dir folder here, all this does is it basically loads the hyperparameters from this YAML dict and then runs the eval function. So let's go into that eval function. And here is where we would basically load the model to fit on the GPU. So somewhere between here and basically here is where we're going to quantize the model. So I think for a first pass, let's just do this. To copy, go over to our favorite friend of GPT, clear our conversation so you guys can't creep on my life, and then put this here. Can you write code, or can you extend this code such that the model is optionally quantized All right, let's do that. And we're also, something I added yesterday night too, is I also added a video model here. So right now we're kind of naively treating this problem as like kind of like an image classification problem, and we're basically taking a let me show you guys what I'm doing. We're taking a pre-trained kind of model, and we're putting it in between basically a channel reduce and a head. So I have a kind of a classification head that, right, is just kind of has a single output. And then I have this kind of channel reduce operation, which basically takes the 65 deep slices and reduces it to a 3-dimension, 3 channels, and that allows it to be fed into a pre-trained model, right? But that's not necessarily ideal, right? It's like these pre-trained models are designed for 3-channel images, and like squeezing a 65-channel image into a 3-channel image and then feeding it into a pre-trained model isn't like ideal, right? That sounds a little bit wrong. So another idea I had is, what if we used a video model, right? So there's pre-trained video models, and what if you think of the 65 slices as basically a video, right? Like a bunch of 3-channel frames of a video. So that's something else we could look at today too, is like, hey, do these video models actually work at all? But let's get back to the actual eval. All right, so here's the actual quantization. You add an additional parameter, quantize. First of all, let's make sure that this isn't hallucinating. Let's try to import this and see if it even works. Sometimes it tells you to import fake things that don't actually do anything. So let's see. Torch.quantize. Okay, that is a real module. That's good to know. You know, sometimes GPT will like invent modules for you, but it does seem like that is an actual real module. All right, so loads model to device, quantize model.eval, model.fuse model, model.qconfig, quantization.prepare, quantization.convert. Okay. Let's see. Inner eval, we're right here. What ChatGPT is telling us to do this. And we're going to need to add a quarg that represents this. So let's add a core here. Let's call it quantize. This is going to be Boolean and it's going to be false, or actually let's set it to get default config. So this is a different quantization config. Let's see what other FBGem, Cross86, QNN pack, DNN. Okay, let's ask these to be described. Can you describe the different quantization available? See if ChatGPT. So different backends here, of course, probably going to depend on what we're doing. Okay, FBGem optimized for Intel CPUs, makes it 8-bit, accelerized, quantized, good choice for server-side deployment with high-performance CPUs. Okay, this kind of seems like what we want, right? That's kind of rhyming with our notebook, right? We actually we delete all of this. Can we do this? Say ls. So I'm trying to figure out what the CPU is for this notebook. Okay. So this is a Cross86 Intel CPU at 2 gigs, 2 gigahertz. Okay. So that does seem, sorry, if you guys can't see, just let me know, because I don't want to be like doing this if nobody can actually see. So this is FBGem is kind of looking like the one we want. Alias for FBGem. Okay, so basically this is the same thing. QNN pack, specifically for ARM CPUs on mobile devices. Okay, so that's not what we want. We're not running this on a cell phone. And then one DNN is a backend by Intel, including CPUs and GPUs. It can be a good choice for deployment as Intel hardware, but it may not be as widely used as FBGem. So, okay, this part here, but it may not be as widely used, kind of scaring me. So, I don't think we're going to use this, right? You don't really want to be using software packages or options that no one uses. You're better off just using the ones that are common. So let's use this one, FBGem. I'm going back to China next month. Can't see those videos. It's all good, man. We'll still be here. Okay. So we get the default config. Does this model quantization.prepare? Prepares a copy for the model quantization, calibration, or quantization aware training. Model will be attached with observer or fake quant modules. Config will be propagated. Model to be modified. Original module is mutated. And then what does convert do? Okay. My cat is going to the vet, so trying to hide. All right, this kind of seems largely fine as well. All right, so it seems like GPT has given us an answer that is somewhat reasonable. So let's actually try. We just try to run this. Image model has no attribute fuse. Okay. Now we're starting to run into issues. Say my. Oops, sorry. That stop generating. My custom model does not have a fuse model function. What should I do? Your custom model does not have a fuse model function. You can either implement one yourself or use PyTorch's built-in fusion functions. The purpose of fuse model is to fuse certain layers of your model together, such as convolutions with batch normalization ReLU. Yeah, so your model is effectively a collection of operations, right? And whenever you're running these operations, sometimes there's operations that you can run them basically at the same time. You can fuse them, right? That's the word that they're using. So it needs to know which are fusible. Fuse modules. Okay. Probably going to ask me to find fuse model. Fuse modules self batch one value in place true fuse module comp2 batch norm. Okay, so you basically have to fuse manually. So let's go ahead and fuse our modules. Go up to our model. Let's implement this. How many times can ChatGPT help you improve? It really does help. No? ChatGPT is very good. Quantization dot fuse modules, and we're gonna want to fuse probably the whole head. No? Probably the head, and then probably the channel reducer. That even channel reduce and head. Clear all outputs and rerun this. Image model object has no attribute model. Not call it that. Oh, okay. I know what's. Here's something tricky. If you guys ever use Jupyter notebooks, you have to restart the notebook if you change the original source file. It's really annoying. And let's eval from episode dir, got an unexpected argument, quantize, let's go here. Let's also have quarks here. basically piping works into eval. Clear all outputs. Start. Yeah. Did not find fuser method for comma. Okay, so not find a fuser method. Actually, turn the false, so we don't want to do this by default. Go up to our image model. This. And let's copy paste here. My fuse model function is not working properly. It throws an error. Can you fix it for me? Might have to actually give it error here. Okay, so you need basically this. Yes. We're also probably gonna have to add self dot model dot model. We're gonna fuse the pre-trained model, and we're gonna fuse our head and our channel reduce operations here. Save that. Let's go back here for all outputs. Restart and run all. Alright, we got another error. Did not find fuser method for. This didn't clear. Clear. Restart. Good here. Image model. Save. Control Shift I to format. Nice. What if we just did this? That should work, right? ResNet object has no attribution model. What? Even need this fuse crap. That's what I'm. Unsupported fuse scheme per channel affine. Problem is these pre-trained models probably have all kinds of crap on them. Let's see if we can find. Okay, so this is a similar kind of thing. It's someone who's using a pre-trained model. He's trying to quantize it. Unsupported Q scheme. Oh, okay. You have to put it on the CPU. Let's see if that actually does. Go back down to our eval. We're going to put this model on the here. So we're going to comment that out, and we're just going to say model equals model dot to, and then we'll say CPU. Maybe that's the issue, that the quantized model just doesn't work on the GPU. Try that. Clear all outputs. Start. Yeah, okay, that was it. Or no. Not implemented. Eval, score, threads, image transform. What? Fuck? Okay, it doesn't like the image transforms. See what ChatGPT got. My quantized model fails when applying a transforms torch vision dot transforms batch of data. A not implemented error. Most of the torch vision.transform functions are not designed to work with quantized tensor, and you may run into errors if you try to apply them to quantized data. To resolve this issue, you should apply the transformations to the input data before converting it to a quantized tensor. Okay, so you basically have to put it before the torch no grad. So here, a patch image transforms of patch. That. Here, all outputs. Save. Restart. Run. If you're just joining, what we're doing is we're trying to quantize our model, see how much worse it performs and how much smaller it is. All right, still running into this error. See, the problem here is that we actually do need this normalize. We can't pre-normalize our evaluation data set because we don't know what our evaluation data set is because we run this Jupyter notebook, right? So we don't even have access to this. Back to image transforms. We have normalizing here. Let's actually open up our input tensor image.open transforms closed. That's very, very similar to what we're doing. Tensor, then normalize. All right, so it doesn't seem like ChatGPT knows the answer. So let's search good old Google torchvision.transforms and quantization. Quantization example in PyTorch. Let's see. So you have your transform here. It's fine. All right, let's look at the actual training code. GD, input data, test, post-training quantization, use modules. Ooh, print size of model. I like that. Let's see if we can copy that little utility function. Where is that? Print size of model. Fuck yeah, let's do that. Copy paste that. Okay, so up here into our little utility functions, let's copy paste. Print size of model. Make sure that the type here is correct. Let's add a type. So this should be nn.module, torch.save, os remove, print model size. Bring that down into our eval. So actually that should show us the size of the model, which will be nice. Let's go back here though, because being average, min max, observer, config, fuse modules. Quantization.convert, quantization.prepare, print size of model. Clear outputs, restart, run this. Send it. All right. So here's the size of the model before quantization. And here's the size of the model after quantization. You see how 334 megabytes to 86 megabytes. So actually, pretty good. You know, it's like 1/4 basically, which makes sense because you're going from float 32, which is 32 bits, into probably the fancy float 8 or whatever it's called. Quantized data types PyTorch. Get the actual name of this. So you can actually see the difference here. So it is going to be a little bit of a drop. And we are doing static post-training quantization. That's what we're doing. We're not doing quantization aware training. We're just doing static post-training. Net, inception. Yeah, it's going to be a little bit worse, but I feel like it should be so much faster that it'll be good. Storage quantization. See if we can actually not implemented error. Rad wrapper. Error while quantizing transformer. Bullshit, no one even answered this guy. Just in time trace throwing an error for quantized model. No one answered this guy either. Shit. PyTorch master documentation. Could it be that the device, yeah, okay, I know exactly what's going on. So this is the issue, is that we are putting the patch on the device here, you see? And here we kind of like monkey fixed it, but really what we needed to do is delete this line, comment that out, and up here where we actually get the device, change it to let's change this function so that it takes a device, which should be a string, and it's going to be none. If device equals GPU and torch.cuda is available, This should be a device in GPU none. Terrible, it's bad Python. If device equals none or device equals GPU, and if torch.CUDA is available using GPU. If that is not the case, then use. And what we're going to do is we are going to change these functions here. So here in the eval, we're going to have to add the device as well. So we added quantize. Let's add an additional quark here. We'll call it device. And we'll say CPU. Actually, GPU. That. And pass that. Control F, get device. Here we want device. And let's do the same thing in the train function. So up here in the training, let's also add a device. Here. Clear all outputs, restart. Don't want to mark down cell, get rid of that. Start. No. Oh no. All of these are right. Our train. Go down to our test. Oh, sorry. Giving it device. What I really want is, so I guess that works. Get device, device, model to device. See if we like hard code this here. Device torch.device. All outputs, restart, and run this bad boy. Model before quantization, model after quantization. Still running into this. Okay, so it's not that our stuff was on a CPU and the GPU. So something's going on here. is necessary to ensure that qconfig in the engine used will be executed. I'm gonna go to the bathroom. I'll be back. All right, we're back. Quantized per tensor, quantized per channel. PyTorch, quantize, transforms, torch vision. Quantize ResNet, PyTorch 2.0, practical quantization. Practical quantization. Quantization per channel. That could be kind of cool. A little medium blog post. Quantization. Do we have transforms in here? No. PyTorch 2. Transforms. Maybe we need to transform, quantize this part too. Let's see if actually GitHub Copilot quantize. If quantize. What the fuck is this? Quant stub. I have no idea what that just is gonna do, so let's see if that does anything. If that works, that's gonna be magic right there because I have no idea what that quant is. Limit open backend fallback. Okay, so here's the next thing we're gonna do. So I don't like that. Very hard to know exactly where this fails because this is a Jupyter notebook. So it's easier to do this kind of stuff with just a script. So let's make a Python script. We're gonna copy paste this. Copy this. Then let's open up our editor here, and we're going to make a file. We're going to call it eval.py. This one is go back to this eval notebook. Let's get rid of our stuff and leave it in paths. Quantization equals false. Device equals GPU. Clear all outputs. Save. Then let's close that and let's try this with just the Python notebook. Or no, just Python script. That means that we're going to be able to go here. This is still that. And let's just run this eval.py. And I feel like this should give us a better error. All right, there we go. You see what I'm talking about? A little bit more verbose, which is good. Quantized CPU, quantized CUDA. Could not run quantized conv2d new with arguments from the CPU backend. This because the operator doesn't exist or was omitted during the select custom build process. Quantized conv2d new is only available for these backends. Okay. So it actually seems like the error is happening. Go to our model. Happening here, I think this conv2d doesn't have a quantization implementation. See what the internet has to say about that, and then let's also see what PyTorch has to say about that. I think the issue is with the conv2d layer in my model. This is the error. Also open up like this. Blah, 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 blah. Hi, I'm also getting the same thing. I have not found the solution. Blah, blah, blah. Only available when you try to run a quantized op with weight or input on CUDA. You have a model 2 CUDA. You are not converting it back to C. Oh no. We're gonna have to use custom quantization models. That's gonna be really fucking annoying. Oh, it might have to do with this freeze here. Because I think here it puts it in train mode, which shouldn't case. Do this right here. Let's do model.model.eval. Get rid of this weird crap. I don't actually know what I was doing. Run this again. Not run quantized with arguments from the CPU. This operator doesn't exist. Christ, dude. Crap. I'm about like 10 minutes away from giving up on this. I think the problem is that we're going to have to use custom quantized PyTorch models, right? It might be the case that the pre-trained models don't actually work and you have to use the like ones that are inside the torchvision.quantized module, right? But that's just going to be so bad. If we do this, wait a second. To overwrite this? Does this need to be this? Model.eval? Is that it? Is that the mistake that we made? Is that as easy as that? No. If we try this on the it's failing on the first convolution. This means you're feeding a non-quantized tensor to a quantized kernel. You need to insert quant stub and dequant stub at the beginning and end of the network. Okay, so maybe here, this here actually needs to go right here, right after we apply the patch. Quantize. And say quantization dot quant stub patch that. Dude, I mean, this is gross. You have to put a quantization layer between each thing? What? That is... It's failing? Failing in the channel reduce module input. Take that, put it here. Say x equals quant x and equant x. Or actually, can we edit equant stub? That works. Missing key channel reduce 1 dot weight, channel reduce 0 dot bias. We need to actually Yeah, we can't do it like that. Because then we can't use the saved model that we have. It's got to be like this. Let's try that. Okay. What I'm saying? Saying, fuck that. We are going to move all this crap. We're going to say screw quantization because it's not playing nice. Back down to our eval. Quantization here. That. And let's just run off quantization false. Twice G quantize false. Make sure this runs. Alright, and we're running on the CPU very slowly. This is the problem. It takes 28 minutes to run a prediction on CPU with a image size that is already 0.05 of the original image. Right? Like if that resize ratio was, look at this, if we do this, size, it's ultimately what we're gonna have to do on that. We need to come merge orgs with H programs. Orgs takes precedent. Yeah, this is outrageous. Look at this. 242 hours. Holy shit. How much is it if we run it on this? It was like 242 hours if we tried to run it on the CPU. If we tried to run it on the GPU, significantly faster, 48 hours, but that's still literally impossible. Can't run that in 9 hours. How much GPU memory is this taking? We could go higher. Let's do a batch size of batch size equals 32. Try that. This might boom our graphics card. Let's see. So look here. This is going to be the GPU memory. Going to quickly grow right now. You know, that's still not too much. We could definitely go higher in the batch size. Make this go down. Try that. Let's do batch size 4. Look here. Starting to get to the limit here. But you know, we're reducing. So you see here how it would have taken 338,000 inferences to predict the entire image. And then if we go down here, it takes 169,000 inferences. So increasing the batch size is an effective way to make the image faster. Formatting. Let's switch over here. Go back. All right, so our quantization experiment was a failure. Fortunately, it was not easy, and it meant that we would have had to redo our entire model, which would have been a no-go. Right, that would have been way too annoying for quantization purposes. I think we can get it to run. We need to, or get it to run an eval, but it's going to have to be a small subset of the image, which is so. What else can we work on at this point? Right? See, I had a list of things I wanted to do here. Crap. Open up my this here. God, come on. Active Subian challenge. Grad scaling, install new computer. Transformer. Oh, that's another one. Wanted to try a VIT here, so. Complete. Why don't we try the video model? See what that actually model here. R2 plus 1D. R sweet. Comment out the. Let's try this video model. See what it does. Sweep.py seed of 0 and batch size of 8. We're using the video model. Training head failed. Shape 8, -1 is invalid. That's the slice that we're doing here. Back, let's model. This view right here. Put a brace here. X dot shape. It's an 8 by 65 by 224 by 224. x.view invalid. Oh, it's not divisible by 3. I know what's going on. I know what's going on. Okay. So we actually need to change keep 60. Comment that out. Comment this out. Make it. Model training failed. Given group 1 weights of size 453177, expected input to have 3 channels, got 20 channels instead. Well, isn't that what the model expects? Back to our source. In our video model, have R2 plus 1D18. Video ResNet. Do this R3D18. Might be model R3D18 not supported. R2 plus 1D18. Let's go back to R. That in there. Torch vision pane. Accepts batched BTCHW and single TCHW tensors. I mean, that's what we're giving it. That is what we are giving it. We're giving it BTCHW sensors. Model training failed. 453177. Expected input 823,224. Is this wrong? It's just straight up backwards. BCTHW. See if we change it manually, if that works. 3 negative 1. CUDA out of memory. Batch size of 1. Expected more than 1 value per channel when training. Dude, what the shit is going on here? Batch size of 4. I mean, it kind of seems like it's working, but is it actually working? All right, well, that's performing inference. Let's do the other task that we wanted to do today, which was making sure that we're not testing on the train data. So, what we're going to do is we're going to go to here, go to our good old friend ChatGPT. Say, can you write a Python script for me that goes through a directory containing sub datasets. Each sub dataset has let me actually put it, mask image called mask.png, label image called label.png, surface volume call it data dir called surface volume width, which contains here 65 images called pro.tiff for each subdirectory. The main directory, I want to create a new subdirectory called trimmed _trim, which contains the same images but with the bottom 10% of the image trimmed. That bottom 10% should be put in a new subdirectory called val. Network error. Copy paste that, make sure it. Generate. Sure, here's a Python script. Here's what you make a new file. Let's call it val. This is really right here. We can actually start copy pasting stuff here. Goes there. Get resize ratio and the resize ratio is. Open mask image. We're gonna need S or PIL from here. We're also going through directory. A target dir yes output dir train or subtest name in dataset target dir. File path is at plus a target dir. And open the mask image. File path. Split, say the bottom 10%. Open labels image. Yep. Here. We're going to say split into train and val. Asking. Then we are going to drop it. Drop. Split. Split. We're going to change the split to 90s. first 90% of the image is going to be the trained data set, and then the bottom 10% is going to be the test data set. Then we're going to save it, and this time we're going to put it in output. Let's say that new file path. Request make sure the new file path exists. And here, call it task. Image mask file path. Here. Call this mask image train. Test or val, sorry. Put that there. Save, and we want the file path be similar. Output dir train and valid. Call this train. Call it split train and split lid. About that. Split train, split lid. Data set. Train file path. Output dir train, and then data valid file path output lid. Make sure exist. Here. Mask mask valid, and the mask image mask train and the mask lid. All right, and now we're going to basically do the same thing but with the labels. So labels train file path, lid file path, up the label image, split into val width and height, label size, crop it, save it, crop it, save it. All right, and now we're going to do the same thing but for the slices. Ugh. Okay. So we're going to have the original slice dir. Then we're also going to have the slice train dir. Make sure that exists. And then the slice valid dir. Make sure that exists. File path. Slice dir. File name. Okay. import TQDM here. Down here. Tab. Say for range 5. Call it num slices. Slice dir, slice file path, convert. Slice original size. Train and val with slice image train. Slice image save. Slice image val. Slice image val. Okay. This script should work. Let's go ahead and into our terminal. And let's try to run it. Let's try to do this. Python make train val dataset. Module object is not callable. Parentheses. Is it from TQDM, import TQDM? Is that what it is? Let's run. Then you go to the bathroom, I'll be back. All right. You know these images are too big when PIL tells you that you might be a decompression bomb denial of service attack, which is like whenever you do a denial of service and you basically send a file that's like a zip file, and then when you try to unzip that file, it just explodes. Decompression bomb. So something weird going on there. All right, let's see our folder and see what it looks like. Let's see if we actually did what we wanted to do. So inside our data, we now have test and train are unchanged. I don't know if I can make this big. So have train. This is still fine. Let's go into split train. That looks also okay. That is looking good. Okay, so if you see now, right? We have a validation data set that is basically the bottom part, and a train data set that is the top part. So we're no longer training on the test data set, which is a huge win. Go ahead and commit that. Call it split. Split data set into original train and validation by cutting the image into top half and bottom half. No, I just don't trust this. Not actually good. I think this is going to be a time. I just don't trust that it's actually do what it is. I feel like that view code that we have is like very sketchy. It's probably shuffling off and a bunch of tab that we. No results. Back to the sweep. Models. Next large. ResNet 101. And let's also add a VIT. So Torch Vision. Models and pre-trained weights. Classification. Let's try an efficient net. Let's try Swin V2. VIT. This one, 633. This one's going to be VIT. VIT. 1 second, I'll be back. Ah, sorry about that. Okay. So we were adding the VIT models here. So there's a couple of different bigger ones. We definitely want these big boys. So get these big VIT models in here. Add them. VIT L30, VIT H4. Add these are sweet. Okay, so we're using all these big models now. There's still a bunch of hyperparameters that we really want to sweep, right? Things like weight decay, size ratio, even the input size itself. So let's back to this. And now on this sweep, we also want to change the, no longer want to be sweeping on test and train. We want to sweep on split train and split the lid. Split lid. And we also want to make sure that, let's also open sweep.ipy and split. And I'm pretty sure right now we're not eval dice score. We're not, I don't think we're even calculating. So let's go ahead and calculate. This score plus equals dice score. The issue. Need to add extra code here to our validation. We can add a lot of like if-else statements to this, or we can make a new function called valid. I think that's probably the better way to do that. Let's make it. All right. Let's not save this. process sample and writing prediction image board. Let's score, or we're gonna label the data loader. Dice the lid. Lid data loader dot original size. F2 call this lid data set. Let's F2 call this lider. Rid of this quantize. Call it lider. Faster, load to memory, sequence sampler, valid data set, those train equal true. But we don't care about this. Print size of model, model device eval, threshold, save. Get rid of this. It's here as well. And on the sweep episode, we don't actually want to eval the lid. That means that we go to our sweep and okay. Let's see if our sweep works right now. So the reason this is taking longer is because it's using the bilinear interpolation. CUDA out of memory. Wanted to try to use the VITL32. Now this is the VITH14. It's probably also going to be out of memory. Yeah, let's do batch size of 8. VITL32 again. Boot out of memory. Boot out of memory again. These vision transformers are really fucking intense. Train. Dataset train. It should be threads. So thread out of that. Oh, I see. There's slightly smaller trans. Oh, these models are a little bit smaller, so hopefully they don't. Okay. Batch size, let's do 4. Okay, so this is the VIT B16. So that work fine there. Our source. I think in our validation, right thing. Lid subtest. Train. Lid on 1. Doesn't take as long now. It's just a minute. And kind of preparing for the sweep that I want to run tonight, right? One of the things I want to answer is how much does the resize ratio matter? So I'm going to be trying out 0.1, 0.2, and then also actually just 0.1 and 0.2. I want to see, this is what I suspect is actually the biggest thing, right? I think if you shrink the image down to like 10% of the image, it's going to be way worse than if you shrink it down to 20%, and so on. But unfortunately, making this number bigger explodes the training time. So even you can see here, right? Performing inference on this 10% image of the second data set is like 6 minutes, right? So it's like all this extra time that you're spending doing that. It's time that you're not spending training. So okay, that seems fine. Just really don't want to be spending like 20 minutes doing prediction every time, you know? So maybe we need to be even more aggressive. Let's do, instead of 0.1 and 0.2, let's do 0.02 and 0.08. Let's make this 0.01. And let's also decrease the number of signals to 40,000 and 20,000. Box. So these results are like, they're going to be similar to the ones before. They're not going to be good, but the whole point of this is not to get the best possible results, right? The point of this is we want to figure out what a good value for interpolation is, for input size, for resize ratio, weight decay, learning rate gamma. Like, that's what we were really interested in, is basically these saving prediction image, post-processing, saving prediction. Yeah, so look at that. Look at how much faster it performed validation when the image size is smaller. So we went from performing validation in 5 minutes to performing validation in 15 seconds. Which is really what you want. Now if we go to our, I'll put dir here. See, look at that. I mean, it's bogus because we haven't trained it at all, but you can see how it's much faster with these. And if we go to our tensor board, getting a dice score, fresh. Should be more here. Predicted images. Why not? We also need to make sure that down here, the valid itself should return or model itself not need that. call this score dict. Over here, we'll turn that. Let's actually go into our validation function here, and instead of returning nothing, we're going to return the best score. So we're going to have best score dict. I have to initialize this. Best score dict of strings to floats. Import dict type here. This. I'll come back over here. Score validation valid score. Here we say write best score. This little bit so it's a little better. Dice. 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 Name of the data set. That. All lowercase. Eight. Best score dict. We'll score name. Here we can add. If score name not in best score dict or score is greater than best score name, best score dict of score name equals score. And then return best score dict, and then let's also make sure that our model, whenever it's actually training, does not do any of this best score crap. So we can get rid of all this crap here. I guess that's fine. I guess save based on that. Okay. Let's say the score is average of back to our training code here. They're all looking good. Let's back to our sleep. Get out of that. Let's run it. Whenever we're doing test mode, let's guys. Is that what I called it? Interpolation, nearest. Nearest is the fastest. Rerun that. So now we're doing nearest interpolation, so you can see how much faster this is. We're training on it. Fast. Now we're eval. No, I guess that's the epoch number 2. Now it's loading. Now it's validating. Now it's loading. Now it's validating. Now it's loading. Now it's validating. And oh no, what do we got here? Iteration over 0D tensor. That means that it did not get added here. Score name not in best score dict. See what the tensor board looks like. Okay, we have 2 epochs of loss. That's correct. We have a validation score for all 3 of these. That is correct. If we go to H params, you should see dice 1, dice 2, dice 3 valid. It's also correct. Error is happening somewhere over. Put a trace right there, see what we get. Alrighty. Zoom in, zoom in, zoom in. Okay. Fordict. Oh, I see. These are still tensors. So we need to add a .val here. Go into our validation function. And here we need to do score dot item. All right, let's try this again. Zooming, zooming, zooming. Validating on 1. Validating on 2. Validating on 3. Done. Okay. Go to our tensor board. Fresh here. Or there should also be losses. Why is there no losses? Okay, there we go. There's your losses. Loss goes up. Fucking weird. That. One thing I'm kind of afraid of is that whenever we did this, messed with files. GIFF volume cartographer. Largely seems like it's working, so we might just end it there. I'm gonna do that. Our stuff here. Let's split that pi a pi. All right. So now the only thing we really need to do is basically just run this, and we're gonna let this run all night. We're gonna copy paste, not copy paste, but git pull on the different notebooks that we have. We're gonna pull on the other computers that we have, and then we're gonna run this on all the other computers, and we'll see what we get tomorrow. Cool. Thanks for listening if you guys have been following along, and best of luck on the challenge.